My name is Beck Martinez. I am the current president. I am here with my officers and a whole bunch of other new faces today. Welcome, everybody. This is a monthly meeting of the Robotic Society of Southern California. Today we have two speakers. Alan will regale us with his current process of his new robot that he's building. And then after that, Jim will give us a talk or an update on his is it a rock crawler? What would you call it?
Yeah, this Chuckosaurus.
Chuckosaurus.
The talk is going to be about hacking your RC car from the intro to hacking.
Nice. Intro to hacking. If anybody has show and tells, let me know so I can add you to the list. I already got you, Sergey. You'll be first today on the show and tell. If there's anything else, we can get started.
I already showed it. Well, I'll go slow.
You got one?
Yeah.
You can show and tell for those of us who
I'll
weren't here.
double it, yeah.
You can never have too much of that.
Okay, all right.
New people.
Yeah, okay.
Alan, if there's another update. Oh. So if you want to take it away, Alan.
All right, for sure. Good morning, everyone. Let me go ahead and share my screen really quick. So in our principal business meetings, we've talked a lot about how many of our talks are on the more advanced side. So I'm going to try to keep this one simple. So this is going to be a beginner talk about serial bus servos and how to use them. To start, I'd like to just briefly hint about some things you're seeing in the news. Honestly, I'm thinking of proposing like a 5-minute what's new in robotics meeting, just because there's so many breakthroughs happening so often. But these types of developments are at the forefront of robotics and humanoid robotics today. They are low gear reduction, brushless servos, which aren't super expensive now, but they're not cheap, or a variant for linear motion. Oodles of processing power. But when you look at the hardware, you're like, okay, it's probably going to be a minute before I can, get approval from the missus or the mister or, from your bank account to do it. But it's simply amazing. And this is state of the art right now. I'd highly recommend you bookmark it and check it out if you haven't already. There's no less than 12 or 14 companies dropping hundreds of millions and billions of dollars into developing humanoid robotics now that these large language model derivative type control regimes are starting to show promise to do real things. So it's kind of the perfect time to be alive if you're a roboticist. About 10 years ago with my InMove robot, which is built just using off-the-shelf servos, I had realized over the course of the project that servos were pretty much a dead end from a robotics standpoint. They operate open loop. You send them a command pulse, and eventually they'll get there at some speed, at some acceleration. And when they get there, the dead zone is between 2 and 4, plus and minus 2 and 4 degrees. So they're not accurate. You have no idea where they are. That's why if you build something complicated with servos, when you turn them on, you have to give them a control pulse to tell them where to go. But if you don't know the initial position of the robot, you get the spazzy stuff, right? So I'm sorry. Yeah, we do for there's no HVAC, so we need a little bit of airflow. I'll broadcast a little bit. Is that better?
Maybe one would be better.
Okay, we can try that.
Yeah.
Oh, those were the lowest. Yeah. All right, so it's a balancing act. So if it starts to get uncomfortable in here or a little bit too warm, we'll kick it back on. But yeah, we're just trying to make it work with no vents today. So I'd kind of written off servos, like they're fun to do lots of interesting projects, but for quote unquote serious robots work, it appeared to be a dead end. Up until about 4 months ago, when the mobile Aloha folks made some waves by demonstrating a robot-like mobile device that through training through teleoperation is capable of doing things that we just couldn't do reliably. You can program a robot to go through any set of motions. Industrial robotics is exactly like that. But in the real world's messy, and unless you're on an assembly line in a work cell with well-defined, input and placement parameters, it is just working. Now, this robot is the Aloha Mobile. It's a mobile version of the Aloha platform that's trained through a combination. It uses deep learning and recording off of 3 cameras, one on each hand and one in the head, and recording through teleoperation. So, they go through the process of cooking shrimp 100 times, 50 times. They feed all of that into a deep learning training, and they train it. And through the magic of neural networks, it's able to extrapolate and perform that task, even when things aren't exactly where you left them. It's simply incredible. This caught almost everyone off guard, including Tesla bot and including everyone else. I have another video that I link in. So this is a dedicated YouTube video that Ben will paste in the chat, showing fully autonomous behaviors. Right now, this platform is relatively robotic. All right. They said that they built it using off-the-shelf components for about $35,000. Now, $35,000 is unheard of for something this capable. I hate to use the word cheap, but when you're looking at like Willow Robotics, and they're $150,000, $250,000 robots, it was incredible. Still out of my price range. Trosson Robotics is actually offering Aloha research kits. They keep updating their page. I think I saw a price on this when I checked last night. So, and it saves you the hassle of ordering the components yourself. And as amazing as that is, it's still not in my price range, right? But it proves something. It proves that servo or servo derivative mechanisms are capable of doing useful work. Servos are back on the table. These are servo bots. These Dynamixel arms, these Robotis arms, the ones that you see on the platform are, are about $7,500. Still out of my price range, but they're really coming down. Dynamixels were the first folks to come out with this concept of a serial bus servo. There's a bunch of stuff that makes them different. But they're higher resolution feedback, they're stronger, they're modular, and actually I think one of my first robotics kits was about 6 of these, and it was like a couple $100, but it was a lot of fun. But for the larger ones, the heavier, the more capable ones, it's still out of a lot of hobbyist price range, people's price range. However, a couple other companies have risen up to offer low-cost versions of these. They're not drop-in replacements. They're actually extensions of existing servo sizes for the most part. But we go from $40 for a decent servo, and these guys offer all kinds of ranges, to $15 to $20. And so that got me thinking. So P-Tech is, I only know about 3 right now. P-Tech's one. High Wonder is another manufacturer of serial bus servos, the servos that are used in the mobile Aloha platform. And the ones that I'll focus on today, WaveShare. So what got me interested in this project was someone on the HP robotics side had mentioned that Waveshare had a low-cost robotic arm that was kind of similar to the Dynamics alarm. It's like $190, so it's not cheap, but you know, I think I can swing that and not have to start for the next couple of weeks. So it got me thinking about what I call it a wish.com version of the Aloha mobile platform would be. And since then, it's evolved to something that only vaguely resembles the Aloha mobile platform. But wait here. After about it seems like forever and it seems like yesterday. Exactly 2 months after I had the bright idea, I was able to string together off-the-shelf components. So we got the 2 arms. No. Let's just trying to remember how the screen works. There we go. Right, the head, the camera, the Seat Studio directional mic. I did have to design some brackets and some 3D printed hands. An off-the-shelf USB speaker and the motorized base from Waveshare. I have something that my intuition tells me could be almost useful. Now, is it tall enough to reach over countertops? Unfortunately not. So I'm going to put useful in air quotes. So useful like secure maybe, both in terms of its hopefully capabilities as well as its height and its strength. So the servos I want to walk you through today in this beginner talk are the servos that are used in the arms on the Waveshare robot. All 3 of those manufacturers use a similar form factor, and this servo is one I have on my desk, and at the end of this talk, we'll go through interfacing with it in Python, and we'll talk about the differences in how you control it and some of the things that make the servo really awesome to work with.
A lot better than the standard old ones.
Yes.
And feedback and all that.
Oh yeah, don't worry about this one. Sorry.
What's the mechanical connection on that? Screw head itself?
The horn? Yeah, the horns are connected just like on standard servos, where you've got usually a screw and then it locks in with the teeth on the third heel. All right, so in this super fancy presentation here, just to compare some of the difference between them. I'm not bagging on servos like you shouldn't buy them. They're a lot of fun. They're super cheap. I've done some really amazing things with them. But here are some of the reasons you might want to convert your future projects to serial bus servos. The first one is feedback. You use the servo object if you're using the Arduino, and then you set it up, and then you send it an angle, and that angle gets converted into a pulse, and it gets sent off in the background, right? So you can send off whole degrees using the standard servo library. But once you fire off that command, you don't know when it gets there. You don't know how fast it's moving. You don't know its velocity, acceleration, or instantaneous position. You don't know if it got stuck. You don't know if it's already there. The commands are fire and forget. And that's why when we talk about servos, we talk about open loop control. There's no, the servo internally operates closely. You give it a command and it meets it. But as you send it commands, you have no idea what the status of the device is. And that gets really frustrating. From the nerve-wracking moment when you power up your little device and you send it its first motion command, hopefully it's not going to swing its arms around or flip over or anything. To anything more than scripting motions, it's really hard to do anything useful, productive with a servo when you don't even know where it is. You can script motion, but it gets frustrating. With these serial bus servos, boy, howdy, do you have information. This serial bus servo operates as a device on a serial network. Now, in the background, it communicates over a serial bus using packets of information. You don't even really need to get into that, but it's two-way communication. You can ask the servo, hey servo, what's your position right now? And it'll tell you. Hey servo, what is the temperature of the MCU in it? Are you overheating? It'll tell you. Hey servo, indirectly based on the amount of current that's being consumed, how much force are you applying? What's your speed? What's your current acceleration? And it will tell that back to you, which opens up all kinds of control regimes and ways of interfacing with the servo. So not only do you get the instantaneous position, you get a whole list of other information. And I'll just really briefly show you to it a little bit. But you get to communicate with it, and it'll tell you exactly what's happening in the servo. Now, in servos, most of the time, their position is being managed with a potentiometer. Potentiometers are great. The Sony Aibo, a very performant robot dog, use potentiometers in the joints. But potentiometers, if you've ever pictured one or seen one in hand, they can't rotate a full 360 degrees. They're at most maybe 270. And then if you force it past that, then bad things happen. For serial bus servos, almost all the time it uses a magnetic encoder that does two things. First off, generally speaking, you get a higher resolution positional feedback. I think down here below. When you're working with servos, you're lucky to get plus or minus 2 degrees when you say, hey, go to 175, which is still kind of a round number because it's not precision. You never know exactly where it is. The serial bus servos use a magnetic encoder with 10 bits of information. So you have a 1024 positions. You divide 360 by that, your angular resolution is about 0.35 degrees. That's something you can work with. Generally speaking, serial bus servos will be stronger. On the micro side, on like the MG90 side, they operate on the same voltage. So they're probably about the same. But this serial bus servos, they're sitting up there, they're 12 volts. So they're already a lot more powerful than 12 volt standard servos. And the big ones, I believe, go up to 24 volts. The ones on Alfie are all 12 volts. I have an asterisk here for magnetic encoder. Wonder does make some serial bus servos with a traditional potentiometer. I think it was a cost reduction measure. The wave share servos all have a magnetic encoder. So not only can they spin a 360 degrees full, you can tell the firmware that there's a gear reduction in place. So if you tell it that the gear reduction is 2 to 1, it'll then interpret your position command on the basis of that gear reduction, which is pretty cool. They're both fast, and to be honest, they're both cheap. Cheap for servos can be $3 to $5 and $7. These servos are about 20, so they are more expensive, but still well within the range of hobbyists like me.
I'm just curious, do they use continuous rotation?
Yes.
With velocity?
With the magnetic encoder versions like these, they are capable of continuous operation. So you have not only positional control, but also velocity.
The Dynamixels had that, but there was a gap in the encoder. So like there was like one, less like a fifth of it didn't have any encoder on it. It was kind of weird there. Yeah.
So yeah, Ben will be kind enough to post these links in case you'd like them in the background. So WaveShare has product pages and wiki pages for all of their products. So good news, bad news, they're super cheap. And there is documentation about everything you need to know. But because they're so cheap, it's not as slick as the Dynamixel documentation. So it's a little bit easier to dive in with the Dynamixels, even though they're the exact same type of a product, just because they spend a little bit more money on documentation and software. But everything is available in their product page and wiki if you're patient. Here, let me see if I can. A second.
Yeah, I was using the initial environment. I remember this. I'm excited.
So there is documents about the protocol. It'd be fun to read through what that was, but to be honest, to get started, I would ignore all of that. But they document in detail. The protocol is actually the same between Dynamixel and the other ones. For obvious reasons, they probably just copied. But their memory location map is a little bit different. But it's the same general gist. Now, for today's demo, so in order to run one of these servos, you need a couple of things. The servos are serial servos, so they need power and ground, and they have a signal line for the serial protocol. For today's demo, and this is all sitting on my desk, I'm going to use this $5 serial bus adapter. It plugs into your computer over USB, and it supports 12-volt input through dedicated lines or through barrel connector. And it also has a UART if that's the way you want to apply. And then it's got two of these connectors, which are standard, but the name is SIGSP, to plug in servos. With the wiring they provide for their serial servos, they say that you should limit the number of servos you plug in serially to 5. That's not because of communication limits. It's based on the projected maximum power draw of the servos and the gauge of the wire that powers them. So,
Do you mean 5 per each of those? Or 5 for this board?
5 for each string, for each wire, yeah.
5.
Yeah.
Amps.
Up to 5 devices.
5
But
devices.
even that, I don't think that includes running 5 devices at full lock, right?
Or
There's,
5 devices at nominal.
5, yeah.
Nominal.
Yeah.
Current.
Yeah, so the way I got around that on Alfie is at the elbow, I split off the power lines and I have a separate power line that goes up to power the lower half of the arms. But there's one single serial line that goes all the way from the shoulder down to the
Right, so you split off the power.
Yeah.
Which you can always, you always need to do almost.
And
Yeah.
all go into the bike battery?
Yeah, so all of those go into a power distribution board that I am both proud of and afraid to show you guys. And that distribution board goes in, is fed by a buck converter.
Oh, yeah.
And then that buck converter has they do a 5 amp. It's probably a 5 amp fuse in line with the battery. So direct battery protection in case things get weird. And that's 5 amps at 38 volts. And then there are 2 other fuses that are run all the way up into the head with the switches because you want to be able to access them. So I have a separate fuse block protecting the electronics rail and a separate fuse block protecting the drag rail. And I just ran lines up through the body into the head to make it easier to get to in case things get weird. But yeah, power, when you're working with things like this, very important to think about. Just because you can plug something in doesn't mean put a little bit of thought. So we'll use this $5 adapter. It's sitting on my desk. I had some power bricks that came with the arms that I plugged in, and then I got one servo plug.
It's much smaller than it looks on the computer.
Yeah.
Like I picture that being Arduino size, but it's like,
Is it 1 inch?
it's tiny.
Yeah, it's tiny,
Tiny.
tiny.
1 inch across?
Put it in your hand in the camera,
Based on that, so.
like side lines. It's very little.
Yep. All right. And just the wiki for the bus adapter. Now, between the wiki for the bus adapter and the general driver and for the servo, there's a bunch of links. It's not super coherent, but if you browse through all 3 resources, you'll find everything that you need.
You know, if there's like a Arduino library. Old school.
Yeah, actually there is. Yeah. Yep, there is. So, yeah. So
He's working in Python.
Oh, I see. So, yeah, C, yeah, like for C,
Yeah.
you know.
Yeah, absolutely. There's the vendor provides an Arduino library for control through an Arduino or any type of a low-level device. And that's what I'm writing for the brainstem portion right now because they're run by ESP32s. For the purposes of today's demo, I have the board plugged into a Windows computer, and we're just going to do a Hello World equivalent application in Python. just to show how it works. But yeah, it's fully supported. The library is not pre-compiled, and much like the Python library, I'm finding myself making changes and updates to extend the functionality once I get my footing. Don't worry about any of that. We're going to use all the standard functions for today. So, all right. So with that as an introduction, let's arrange ourselves right here. All right, so I have a camera set up. I've already downloaded their ST servo Python library. And that library is divided into two parts. They give you some examples, even though they don't clearly state it, about how to use the servo. These are just straight Python. We'll look at them in a second. And then when you want to get really down into the weeds, the low-level stuff is all in their ST servo SDK object. And so these are the mechanism by which it leverages that serial protocol to allow you to do interesting things with the servo. So here's how I'd like to approach this. I prefer not to spend a lot of time draining each slide, but I want to give you the feeling of and the intuition of how to work with this and how the servo works and how you'll work with the servo for your next robotics project. Because I'm pretty sure by the end of this talk, y'all are going to switch to serial bus servos. All right, so the first thing I'm going to bring up here is ping. For those of you as nerdy as I am, you know that ping means I'm just going to say hello, and that device is going to say hello back. We do it on computers, on the internet. I think it's a poke on Facebook. Do they still poke people on Facebook? I don't know these days. I don't use Facebook. All right, so here we have a whole code, a whole program. Now I'm going to fancy this up a little bit. I want to copy all of this, and I'm doing my coding in Visual Studio. If you have a favorite IDE for Python, that is totally okay. Most of this will still apply to your IDE of choice. I happen to think Visual Studio Code is one of the best free IDEs available on the planet everywhere forever. Aside from context, right-click, highlight, surfing through code, autocomplete, integration with Microsoft Copilot, remote access. It also supports Jupyter Notebooks, which is a really fun way of creating and interacting with Python scripts. And so I'm still going to call this a beginner because I think this is a valuable tool to add to your arsenal. So what I'd like to do is open up and create a new Jupyter Notebook file. And I'm just going to paste all the code, which you can do. That's fine. That's fine. Now, so why even use a Jupyter Labs notebook? Well, when you write a Python script, and every time you save it and then you run it, right? That's the cadence, right? Save, run, crap, and error. Save, run, crap, change a variable. Which works just fine. And you can do that through Visual Studio Code. Once you tell it what Python interpreter you want to use, you can run the code directly through here, and that'll work just fine. So, but I am going to move this into Jupyter Labs just to show you some of the benefits of that. Now, right now we have one code block from top to bottom, and the same thing. I can click on run, and it'll run just fine. But there's one thing we have to do first. The serial driver board is plugged in to the computer through USB. As of right now, we don't know what COM port it's on. The serial UART shows up as a COM port, both in Linux and Windows. So let me show you how to figure that out on the Windows side. So we'll go to this PC, right-click, show more options because we're on Windows 11, and manage. I thought I had this open, but it must have closed. So we'll go to device manager. We'll get a warning, we're not logged into the admin, so don't trust myself not to screw anything up, that's okay. And then what we're looking for is ports, COM and LPD. This is the only part that's a little bit weird. At some point, someone will think of a faster way of doing this. But I need to know what the COM port is. So let me open up ports. And I can see that that driver is showing up as COM3. So now I know where it's hiding. You could also go COM1, run crap, there's an error, COM2, crap. That would also work, right? But to be legit, open up device manager, and then once it's plugged in, you'll see it show up here. All right. So that's for a ping example. Let's start separating these out into code blocks. So I'm going to put the cursor right here. We have a whole bunch of comments, which is nice and it's pretty. And then we have some reports. I'm going to put the cursor right there. Right click. Notebook. Oh, wrong one. Right click. Notebook cell. Split cell. All right. So now we have a cell up on top just with comments, which can be evaluated separately, but there's nothing to do. And then we have a second cell down here. So we're going to start splitting our code into sections. And what's nice is that once a section is run, it stays in memory. It doesn't exit out and release everything. So you can iterate more quickly by separating your code into sections and then evaluating them separately. So we have comments right here. We've got some setup. I'm not going to go through any of this. I don't even really care how it works. It looks too complicated for what it's trying to do. But I want to put that in its own section. So notebook cell. There's probably a keyboard shortcut for this. And split cell. All right. So we do have some setup here. So I'm going to run the cell just on its own. Click on this little arrow here. It says execute cell. And it's done almost instantaneously. So we do a couple of setup functions, and then we import that ST servo SDK. Now, in the next row, it looks like we have some setup. We have a constant STS ID, 1. That's the number of the servo that we want to communicate with. This is one of the coolest things about this, is that you can string these in serially. Each servo has their own ID. And that's something that you set when you first get it, and you can run a program to set that. So you can have 5, or in this case, 7 servos all on the same serial line. But when you communicate, you're like, hey, servo 1, what's your position? Hey, servo 3, move to this position. Because each servo knows its own ID. And so the one that I have on my desk here is ID 1. So we'll leave that.
Is there an app to do that too, or?
For Dynamixel, they do. For the cheap ones that haven't written the app yet, you write a little Python program. Okay, to swap it. Yeah, I'm skipping over a few of the things that are a little bit.
Change the ID.
Yeah, change the ID. It's not hard.
It's much like CAN, like the same thing. You have CAN IDs, you have to set them all.
Exactly.
Remember and write them down.
Exactly. The second one is the baud rate. So your devices have to agree on the communication speed that you're going to talk to them with. If they don't match up, you guys aren't going to understand each other. By default, these guys are set up to communicate at a megabit, which is actually, it's a lot of bandwidth. So we're going to leave that as the default. And our third constant here is what COM port you're using. We'll change this from COM11 to COM3. And then let's see, some more boilerplate. There's something that opens up a port. We succeeded or not, set port baud rate, set it or not. So this is just more setup. So I want to put another break in right here, just to separate out the code. All right, so if everything's set up correctly, this block of code sets up and opens up the communication port to that servo port. So let's run it. Oh, and that's it. We opened up the port and we changed the baud rate. Very good. Okay. So this third section of code. What's also nice about this is when we go to the next one where we go through how to move the servo, 3/4 of that code is the same. We're not gonna have to copy the whole thing. We'll just copy the meat of it. All right, so what do we have here? Copilot's offering to be helpful, not helpful right now. Hey, guys, come in, yeah. Grab a place.
Yeah, this is fine. Thank you.
All right, so without going through and trying to figure out what this code does, it looks like it attempts to ping the servo. And if it's able to, you get this message, ping succeeded, with nicely formatted. And if the error object that it passes back isn't 0, it'll show you what the error is. So let's just go ahead and run that. We'll see what happens. All right. Ping succeeded, SDS servo number 777. And then finally, the last thing that it does is it closes the port. Let's separate that one out as well.
How do you do that? You just, to split the cell, you put the.
Oh, yeah, I just
You're
put
just
the
putting the
cursor
cursor at a point and then
And then
split.
right click, no put cell, split cell.
Oh,
I'm not
okay.
smart enough to memorize the keyboard shortcut.
Everything below that gets split and then you.
Yeah, upper and lower. And what's nice is we can go through and we can run each of the individual pieces of code separately. So that's what makes this a lot of fun. Let's go ahead and save this so I don't lose it. All right, so there's a lot of boilerplate code. I don't care about what most of it does. But this is kind of your hello world example, just to make sure things are set up correctly. Now, and of course the servo doesn't move because we haven't told it to do anything. Let's look at another one of their demos called Right. And we'll scroll through a lot of the same boilerplate. We have some different values here: minimum and maximum position, moving speed, and acceleration. And then, so this one definitely moved it. So let's do this. These guys. Let's just copy that. And let's add that underneath here with the rest of our stuff. And port handler, blah, blah, blah. Okay. And then it does something. Let's grab the does something part. And paste that in here. They've got some goofy press, print, blah, blah, blah. I don't care about that. Let's comment that out. All right. So we'll rerun the section that defines those new variables. Or can we not that long? There we go. All right. So just reading through this demo right off of their website, it looks like we write a position. And then if we get a success, awesome. And then if not, we show you the error. And it switches back and forth between two goal positions, which are the minimum value and the maximum value. It's a little convoluted way of doing it, but that's all right. It's there now. So, right position X. Let's take a little bit closer look at that. So this is another it's a good point about serial bus servos. So for their right position X, when you talk about servos, you just give it a position, fire and forget, maybe it gets there, maybe it won't. These guys are a lot more advanced and not complicated, but they have a lot more capabilities. So with that goal position, you can communicate three things: where I want you to go, how fast I want you to move there, and how fast I want you to accelerate there, right? So this is very similar to the control method for the brushless servos for the humanoid and the dog robots. Their controllers always accept and you can do it by velocity or force as well. But when you're communicating these, it wants to know where you want to be, how fast you want to go, and how fast you want to accelerate with every command. So you have control now over how fast you want it to get there. And as part of your control regime, how you choose to control your robot or your arms, you can take advantage of that. So you can program in, hey, if I'm moving something heavy, move it at a slower speed to this position. Or in my robot's case, I'm very top heavy. So when I'm starting to move, start to move slowly. We use a slow acceleration so you don't topple over. But that's one of the many cool things about serial bus servos is that whenever you command it to do something, you give it all three pieces of information. And then when you get a little bit more advanced, you can pull that motor and see exactly where it's at. Is it there yet? Is it still moving? What is its speed at? What is its current position? So cool. So cool.
Is there like speed ID type in there somewhere, or you?
Yeah, there are. Let me see if I can. Here is, and this isn't something I would worry about when you're first getting into it, but all serial bus servos are set up like this. They call it a memory table or a memory map. I think it's because the initial ones were 8-bit and they wanted to simplify it. But your communication, your low-level communication with the servo is by reading and writing values to these memory addresses. And some of the memory addresses are, each one's 8 bits, 1 byte, but some of them have 2 locations for 16-bit and some of them only have 1. And so just scrolling through here, we've got some easy ones, things that you would only read, right? The firmware, major, version, sub number. Now, here's the fun one. When you change the ID, you'll be writing a change to this memory location to change the ID that the motor responds to. Baud rate, return delay, most of those you won't touch. You can define minimum and maximum angles in the firmware so that if you command it to exceed that, it won't exceed it.
You don't have to put that in your code.
Exactly. You can tell the servo, and the servo will help protect you. There's a temperature limit. I don't know what it's set as a default. It's 100. To say, hey, when the servo exceeds this temperature, shut down. And it's already baked into it. It's already baked into that. One of my first projects, I was overusing a servo in the head for a head that was altogether too heavy. And in the wrong position, it would overheat and it would shut down before there was any damage. Traditional servos, they'll catch fire. They don't care. There's
I have clutch ones that I
Oh, really?
I bought DF Robot clutch servo. They show the guy holding the servo in a 9 gram and like twisting it while it's on, and then it basically clutches and it's not broken.
Yeah, I've probably set
cool.
fire to about a dozen or more
Actually,
servos
fire?
in my life.
Oh, because it heated up.
Because there's no checks and balances. If you command it to a position that it can't reach because it's
Yeah,
stuck,
yeah. That's
it'll just go at it.
So I have a clutch one, and I commanded it to a place that the cable was caught, and it for a couple of seconds it stayed there, and then it just de-energized. It's really, I bought those on a whim a long time ago, but clutch servo, that's
Yeah, so these guys will not overheat. When they hit your temperature, they'll just shut down. Probably not super convenient if you're doing something important, but at least you won't have to replace it. You can define a maximum torque value to say that torque values over this amount it won't honor. Just all kinds of stuff. You can define custom PIDs for the internal control right here. I haven't looked into that yet.
that's internal.
But they are available, yeah, to control how it. Minimum startup force, counters, instance of protection current. Most of these I don't know where they are. Protective torque, speed closed loop, P&I. Target location, when you send it to a location, these are the 2 values that it populates. Running time, running speed, lock mark is it currently moving, current load as inferred by the power that's being drawn Droid across the driver. Servo status and current. So yeah, all these are available to you to understand the state of the servo. But the short answer is, yeah, they do give you the ability to change those in addition to the velocity acceleration curve.
Yeah.
All right, so we've got everything open. Let's look at a little bit of a code right for the demo. We're basically writing two positional values. And then, yeah, let's run it and see what happens. Yeah.
There it goes. It's the opening port. Opening ports always takes.
Oh, because I broke out of it. It's close apart. But there's no air.
We just saw it move. It's the caster version. What? It moved right when it canceled it. Oh, that's
Oh, I think I know
important use. They tried to.
I think I know what's going on. All right.
Did it open twice?
There you go. Okay.
Serial ports
Let's clear all outputs.
can be nasty. It like gets stuck.
Our bottom one is closed port.
And don't close, I have no.
Yeah, that's-
I always had that part, but you control the
C
safety
handler,
handler,
so when you control C, it closes. I put that into all my Python. You know, if it interrupts, then
They close things.
and close whatever, not just servos, any serial, anything that has to be closed. So that control C always does the cleanup.
What's going on, buddy?
Shouldn't, not that, that's part of it, wasn't part of it. In that one block.
No, that's only at the very end.
Oh, yeah. Oh, there it goes. Oh, what did you?
What's going on? What did I mess up? So I blocked out these.
What does it say?
I think the port was still open and then it finally timed out, it sort of worked.
Yeah, something like that. Wait, but now you'll have to start from the beginning. I think you might want to start from the beginning,
Yeah.
like let it cancel out and then start from the beginning, open port and. Oh,
Yeah.
oh, then there's that. That kernel thing can get confused.
All right, so let's get rid of this first part right here. We'll just delete it out. While one, wait position X, clear all outputs. Let's just do a run all.
Oh, what breaks it? It doesn't break.
Oh, I know what's going on. I know what's going
How come it's wow one?
on. I know what's going on.
Oh, it's supposed to just do an infinite loop there, right?
Okay, yeah, this is a little embarrassing, but it's an infinite loop.
On purpose.
And this little piece right here, press any key to continue.
That's important.
That is the break that gives it a chance to move before you move to the next step. So,
Wow.
all right. I think we're,
Yeah,
let's say, I did
because
something.
you're giving it continuous commands, aren't you?
Yeah,
About that.
yeah, that is why you don't make last minute changes, right?
We just learned something
We all learned something.
about
Alan isn't nearly as smart as he looks.
it. Purely programming, or can you press? You have to take keyboard input. No. In Jupyter?
Yeah,
Does
you know
that
what?
work?
Yeah.
Is there a way to do that?
Let's do
You could just do a sleep, right, or wait, a delay, or in Python, a time dot sleep.
Let's try that and then we'll just move back to our normal one.
You can put it back in somewhere.
Yeah, I mean, but for
But
this,
it's not made.
for Jupyter Notebook, though, you can't have it like get character, can you?
Do we have a delay in Python? I don't
Yeah,
think so.
time dot delay. I'm sorry, time dot sleep, and import time. If you didn't import it already, and then you give it a number in seconds, so,
Seconds?
yeah, so whatever, like 1 second, and
Oh,
however many seconds you want.
Let's say a few seconds.
Yeah, a few seconds. Of course, that'll wait on the first time 4 seconds. There you go.
Hey! Are you not entertained? All right, so yeah, sorry about that. That was all self-inflicted problems. So it's writing the following two positions with this velocity and this acceleration. And again, these are just demo programs to give you a feel for how to interface with the servo. But the servo just isn't a dumb device like a standard servo. It's an intelligent peripheral. And step one is aside from your hello world and sending commands, is to come to terms with having control over the position, velocity, and acceleration for all of your commands. And then once you get a handle on that, then you can start setting up more state machines to be able to read back the instantaneous position. If you've got a more complicated robot and you have like a visualization of the robot in ROS, like RViz or VoxClub. Hey, how's it going? Hey, that means something to see you again. It's been too long. Good.
I want to comment how smooth that's running compared to a regular server. Regular server like jump over and then like at the end and just all the nastiness. That's so nice for a robotic.
Yeah, this is I know like an hour of prep to watch a servo thing, but like to keep it as beginnerish as I can, like this gets your feet wet and this gets you interesting things. Getting back to the more complicated the ROS and the robot visualization in there is you're able to visualize the robot in ROS, not with the position that you send it to, but you can report back the position that it's actually at. You can see it move in real time because you're able to get that real time position back from the servo.
So are you planning to close in ROS?
Oh yeah. Yeah, now that the hardware design is finalized, I'll take the design and move, actually my workflow this time will be to move the Fusion 360 model into Omniverse, articulate it, set up all the joints, and then export that Omniverse formatted robot back to Erdif. The challenge is there's a lot of detail in here. And Erdif models are generally very, very simple. So I need to find a way of simplifying the parts. Not that the computer can't render it, but there's no point where the graphics card can render 100 million polygons a second and make it look super awesome. The Erdif SPLs need to be vastly simpler. That's what I haven't figured out yet.
Oh,
I wrote a bus servo driver for ROS. So
Oh yeah.
if you get there, yeah, I forget why, but
you had to write one?
yeah, either they didn't have one or I didn't like it or it was too slow or something, and so I wrote one.
Good for you. We'll be downloading.
Yeah, absolutely.
Right on.
Yeah,
So,
because you need, if you want this in ROS, you want a driver for this stuff in ROS,
yes.
ROS 2.
So instead of doing your time dot sleep, could you like just pull for 0 velocity and like change once it?
Absolutely. That's a very good point. If you wanted to be even, clever about it, because you could ask the servo, is it moving? Has it reached its target position? You could write a loop that instead of waiting for sleep 4, like I'm doing because I'm being super simple, is to have a loop that pulls the servo and says, hey, are you still moving? Yes or no? If the answer is yes, sleep for a millisecond or 100 milliseconds and then try again. Yeah, now you're thinking like a serial bus servo guy.
Can
So,
you write a loop that'll just make it go continuous? Just continuous. And what would happen? Yeah,
I'm not sure, maybe during break you can try that, but yeah, these servos are capable of continuous operation. They use a magnetic encoder, so they're not limited like a traditional potentiometer. And they do accept continuous rotation velocity commands. So, yeah. Yeah, you do a lot of fun stuff with it. So to take this back home, there are 7 servos in each arm, and then there's 3 in the head of, let me go bring up the Alfie graphic. So there's 3 servos in the head because you can't cop your head to one side, then what's the point? There are
I think Alan likes this, because it looks a little more like the Delta printer that we got. Got the same, but like on one side of the Delta printer.
That's actually a Super Racer Delta printer.
It is, huh?
It's the lower cost one.
It's a 3D printer turned into a robot.
It is, it's like a one side of a 3D printer,
Or
part of a robot, yeah.
Yeah, so each one of these arms of 7 servos is connected to a general driver board with an ESP32 in the base, right? So there's 3 levels of computation happening in the robot. The ESP servo board, the driver boards, communicate directly with the servos, right? And so you can run the hello world code and you can write the Arduino code to move them, and it works just fine. These servo drivers are connected over USB to it's like a Raspberry Pi IndyDrive building board that has 8 cores, 16 gigs of RAM. It's one of the beefiest versions I could find, right? So we're going to use ROS to facilitate the communication between the main computer and the ESP32 microcontrollers, right? So we're coming up with messages that look similar to this. For the movement, tell me where you want me to go, how fast, what the acceleration is. There's a similar set of messages for the wheels as there are for the lights in the head. And then after that, what I'm calling brainstem code is all in the boilerplate. Then we can start writing some programs that make the robot come to life. So it took me about 2 months from, hey, this sounds like a cool idea, to burning my fingers for the last time with a soldering iron. Construction's complete. Maybe 2 weeks for the boilerplate brainstem code. I'm just calling it that because it's not code that does something. It's code that allows you to do something with it. And then things would get interesting. Based on the work and the progress with these heavy-duty humanoid robots, I see no reason why some or all of that can't also be applied to an Alfie-style robot. So the Aloha mobile platform is $37,000 as a kit from Frost Robotics. This guy, if you subtract out the dead ends and the extra parts that I purchased, if you're like, oh my God, Alan, I want to build an Alfie, and I give you the bill of materials, it's about $2,100. So it's not super cheap, but it gets your foot in the door to play with some of the most exciting robotics topics and concepts and applications that I've seen since I was a kid. Yeah,
Got the microphone on the top. LiDAR
yeah.
Or the.
Yeah, so no LiDAR on this one. I'm using the depth camera
Oh,
from,
yeah. Front
from the
panel.
Alfie. Yeah, which should give you enough information. And then, yeah, the microphone on top, the little top hat, not only gives me raw audio, I believe it gives me filtered audio. Okay, so the Jim would keep me honest. As well as direct. All kinds of fun stuff. It was just a matter of integration. So this is the systems integration phase where I bolted everything together, and now I gotta write the code to make it work. So yeah, so that's all I've got for this week. I'll be here. We'll probably head back here after the break for lunch. I can answer any questions about Alfie or serial bus service. All right.
Just a little bit in late. This is monthly meeting of the Robotics Society of California. Just to talk a little bit about the meetings. They're all free. You don't need to be a paid member. But if you do like what you see, we do ask that you guys consider a paid membership, which is $10 for the entire year. If you do, you can come talk to our treasurer, Ron. He will let you give you all the information you need for that. The paid membership, it doesn't really do anything other than you're a paid member, and you can vote in the elections. Other than that, it's completely optional. You don't have to, pay membership. You can join every meeting, participate as much as you want, for free. And we're here on the second Saturday of every month. And we'll say after that, Jim, are you ready with your talk?
Yes. So today, I'm gonna talk about hacking your RC car, which I've been working on for a month and a little over a month or more. And I'm working on a project for robo games using this RC car from Traxxas. And for robo games, it's next week in Northern California. By the way, my name is Jim D'Annunzio. I'm a software engineer, career software engineer. I work for Samsung TV video display division for Samsung Research America. And I got into robotics with this club in around 2015 and watched many lectures, attended, and then started building my own within a couple of years. And so now I'm like vice president. And I wanted to participate in competitions when I could. And so I went up to Robo Games last year in Northern Cal, it was Pleasanton, in the Bay Area. And Robo Games is a big event. It hadn't occurred since 2018 prior to that. And it's occurring again this year in San Jose Convention Center. It's a $60 to attend it per day. It's a little pricey, but if you enter a robot, it's $85 for the whole weekend for all the days. So I'm entering a couple robots. This one is called Robo Magellan. I'm not sure it's gonna be ready in time, but Robo Magellan is a contest where you use a GPS and on your robot, and it's outdoors, and it has to navigate to this destination traffic cone all on its own, autonomously. So that is like the goal, and a few of us here are working on that. So with that, I'll start introducing what I did initially, and several other people here have done this before. And on the internet, a lot of people have taken these RC cars as a base and turned them into autonomous vehicles. And I'll show you why that is a convenient thing to do. And it's a little pricey. These run $370, or I always buy things on Black Friday, so you're going to get some discount. But there's various prices for these cars. But as a robot platform, so much is already there for you. The motors, the wheels, the suspension, everything is remote control, and they are surprisingly relatively easy to turn into an autonomous vehicle because of the standards they use. So this is what the original looks like. By the way, mine is over there. You'll see pictures of it online here as we go. But that's the physical robot. So this is what it looked like when I got it. You can see there's, I guess I should use the mouse here. You see there's some, I'm going to be putting on electronics into this device. So I need some space. And so you see there's some flat areas here, and that's what I end up using. This is the ESC, electronic speed control, and the motor. This is a single motor that drives all four wheels. This is a four-wheel drive car. And through linkage, the single motor drives all four wheels. The battery goes in this little spot here. The electronic speed control is what handles the motor. And over here, you can't see it's covered, but this is the receiver for the remote control 2.4 gigahertz remote control. That drives the steering and the motor. And we'll see how we're gonna hack both of those. Here's another view, of the car, so of the, untouched car. So
Yeah.
now,
Oh, Jim,
yeah, and
one cool thing about the name Traxxas is the brand name is that the quality is pretty decent for stock vehicles. So I've used a bunch of these.
Have you, oh,
A lot of them, yeah. So this is a good, good choice. So.
right, and they're pretty sturdy, and every hobby store has a car, so you.
Yeah.
Like a liquid charm, you go down the street, pick it up for $5 and drop it moving again, it's like
And
mail
you
ordering
You
and.
can change everything to aluminum, by the way. Go on Amazon, every piece you see there, you can change it to be aluminum if you want.
oh, the whole
Everything,
frame.
anything that you see.
Wow. Yeah, so there's a lot of support for these because
A lot of it.
there's potentially, well, I don't know, 1 million people out there who like to use their RC cars. This one's a crawler. It's not designed for speed, but to go over rough terrain. And that's partly why I bought it, because of the potential in Robo Magellan could be over grass and sometimes you go over a curb without even realizing it because you're using GPS coordinates, etc. And it can go slow, which is another kind of recommendation I got for a Robo Magellan is you want to be able to go slow when you need because a lot of RC cars, they are designed very fast and it's a hairline trigger and it will just go off so fast. So that was the recommendation. But other people, you can use the faster cars. You just have to be a little more, aware of that. So here's the beginning of some of the hardware changes I've made. I guess, yeah, I'll show you piece by piece, but so a microcontroller is necessary to take over control instead of the receiver just sending the pulses from your remote control. You want to control them via a microcontroller. So this is a Teensy 4.1 in a 3D printed case. And as I said here, this is the, I have another picture of it uncovered. This is the, where the receiver is and the, where the servos plug in the original car, both the steering and the drive motor plugs into this. So I'm kind of hacking into that. On the right here is an IMU, MPU, inertial measuring. So that gives the acceleration. It's a 9-degree accelerometer, and a gyroscope and a compass. That is to help know where the car is and what its orientation is, and that plugs into the Teensy as well. Over here you have the GPS module, which is, we'll get into that later. That's going to be how I know where I am outdoors. And then, of course, the main brain is Raspberry Pi 4B here. And now I'm skipping over, but I had to figure out a way to mount these. And luckily on these cars, there's sort of unused screws. You can see here there's these screws that keep this cover on, but there are other ones that are unused. And if you take off some part, like I took off a part, this railing here is removable by these 4 screws. So I didn't really need this. I mean, it's helpful to keep your robot in real rough terrain from damage, but I decided, for Robo Magellan, I'm not expecting that level of rock climbing. So I took this off and I was able to use these mount points to mount electronics on that side anyway. And then this Teensy kind of just wedges in there. It's not even screwed down, but these other ones are screwed down. And that's what it's nice to make a case out of a 3D printed case. And I'll show you, a lot of these are downloadable, or these are all downloadable, these cases. And then I modified them to fit my needs. So the Raspberry Pi is there. That's the main brain. And using USB connections, power the other, the teensy comes off, it's powered by USB, as well as other things. Actually the GPSs as well. Now here is where I needed my own power supply for the electronics. I did not tap into the main battery, which is an option. Some people do it. The main battery, if you do a little more advanced work and get a splitter and a buck converter, then you could do that. In the time I had, I decided I'm very used to these power banks. So I installed a tray in the back and have this power bank that has 5 volts. And that keeps that powers the Raspberry Pi and some of the other electronics conveniently with a separate power supply. Now, like on the underside of the top frame, you'll see it's a little bit of a mess of like long cable. I didn't have time to really cut these cables, but if you secure them all, with tape and whatever, you can kind of manage this. So, because I need to take the top off to replace the battery, to charge it, and to press the main button to turn things on, to turn on at least the main power for the ESC, which is here. You have to press this little button to turn on the motors of the robot. But for my electronic control, you just like kind of lift the back and there's a button here that turns on the power bank. So that part, we don't have to lift too much. And the other thing I did was install a bumper. This is a sensor that if I hit something, I'll get feedback, and that goes into the teensy as well. This bumper I got from DF Robot. It was part of my Big Orange project, but you can buy, I think DF Robot may still have those. And that's just a way to know if you've hit something, and then you can, it's the last resort of obstacle avoidance. The other thing I did, so going through all the mechanical stuff first, obviously, or in a mix of electronics. So here's some more mechanical things. I needed, on the front of the robot is there's a camera and a mount of a pan tilt mount. And I guess I didn't show a picture of that. This is what it looks, this is what the whole robot looks like. And so you've got a LiDAR mapping system on top and this OPD camera on the front, and it's got a pan tilt servo as well there. And so to do the cabling, I drilled a hole and had these little gasket rubber grommet, yeah. And I just thought I got to use that. It's perfect. It will keep the things from, keep the cables safe. And it was just big enough to put through a USB-A connector through that, or an Ethernet RJ6 or an RJ whatever connector. And then here's the one in the back. And I conveniently put them in the windows of the car, so they're kind of, I like an aesthetic appeal to not wreck it too much. So that's that part. Another important thing that I got into for this project is a DuPont crimper. I've been, for 6 years, I've been using standard length DuPont cables that you just buy. And by the way, the DuPonts are what you see here. All those wires here are DuPont, but they come in different lengths that you buy, and they could be too long or too short. So finally, I'm like, nah, I want it very clean in there. There's not much room. So I bought this and learned how to crimp. And my first few, you kind of mess them up and you throw them out, and you have to test every single one you make to make sure it's, like, I made a couple and it's like, looks perfect on the outside and there's no continuity. It doesn't actually connect. So anyway, but
That's pretty high on my list of things I hate to do. I have all the gear and about 80% success rate with this.
yeah, I just started, but you know, I assumed I would have some mistakes, and hopefully they're the ones I put in there are working. I even did like a 3 cable without separating all 3, like a servo extension. And boy, it's a pain because, yeah, but anyway, it's worth it to, I figured I need to learn this. Other people have done it, and I think it's very useful skill to have.
Yeah.
I don't know if you've
Very, very frustrating.
Because-
And there's, oh, I'm saying that DuPont, there's DuPont, these are DuPont, everyone's a little different, every crimper is a little different. You'll get different success depending on which exact connector you use. It's very frustrating.
Yeah, so I bought this kit. I guess I should have given a better picture, but this kit comes with the crimper plus a box of all the things you need, and it has instructions as to, like, you need to use this last crimper part of the crimper there. The I don't know what it's called, but that one is the one to use, and it shows you how to, you know, insert it a little bit inside, not from the outside. Anyway, so it's just this tiny little pamphlet that tells you, and then you just have to practice.
How much did the printer cost?
The crimper with the whole box of stuff, I think it was $30. It comes with like
That's not bad.
all the connectors you're going to need for a year, or I don't know, maybe multiple years, with female connector, male connectors, wire, and it also came with, what's that? Housings, and this one also came with the another box of those what are they called, the JST connectors. So those, you can have the female and the male, and those little white connectors. So you could create those in a robot. I like modular design, and I don't like soldering stuff that I may want to change later. So that's why
I still solder it.
you still solder. I don't want to have to.
In the one time that I did not solder, the connector came out and I didn't know what the problem was until I
Yeah.
troubleshooted.
Like on this modification, I didn't want to solder, and but well, yeah, and I was worried about these wires here being, you know, loose,
Yeah,
because
those.
it's just
Those will get
it's
loose.
just you know, these are just DuPont connectors. But what's fascinating, or what's interesting, is when you print these cases, it leaves a very tight small amount of room here for these pins. And when you put these in that situation, they are solidly in. You cannot, they will not jump out with the bumping. You have to pull with your hand.
Yeah, they still.
Perhaps,
Yeah.
a bit of ghetto advice for you. Do you have a hot glue gun?
Hot glue gun or,
This experience would like to recommend that you invest in a.
I do have.
yeah.
If you use bigger connectors and you get more pins on one connector, it's less likely to come out. So even if you're doing one wire, if you have like one of those sensor boards, use all 3. It's a lot.
Yeah, also, like when like this cable here is a three socket connector.
Yeah.
Some of them are ones, or whenever I can, I use multiple ones.
And as long as the device doesn't move very much, you should be okay.
But like I'm, but I'm telling you,
Some vacuum. Vacuum container, you'll be okay.
well, yeah, like I said, when you tug on this, you have to pull quite hard because it's wedged in this case. You understand what I mean?
I hear you.
In your defense, Jim, I'm using these and I crash my car all over the place and they're not falling out. Because I think they're so light, as long as you get a decent, you know.
No, right, oh yeah, I may use the glue gun, but you know, at this point, it's lucky if I get the project, you know, to do what it's supposed to do without worrying about wires popping out, but I mean, you know, it just is very cool that this combination of having a case and slightly wide DuPont connectors. It wedges pretty good. And then you could glue gun on top of that to really make sure, which sounds like it's a good idea. So then, moving on from there, here's a top view. Now I also bought a powered antenna for the external. So this is the GPS external antenna. I just figured you might as well do it since the board supports it, and you should get better reception, or the best reception possible with the. It's a 3-volt, I think, and it comes. The board supplies the 3 volts for powered antenna. Now, oh, here, this anything else I want to show first? Oh, so here are the components. You're probably all familiar, or many of you, with the Raspberry Pi 4B, the main brain, and that's running Linux, Ubuntu Linux, and well, ROS for the higher level. We won't get into the ROS in this talk. I'm only going to cover the sort of the low level Arduino code or microcontroller code. Here's the Teensy. The Teensy is powered by a micro USB that plugs into the Raspberry Pi, which also communicates that way over serial. So so that all the commands can come from Raspberry Pi to when it's ROS enabled. With just the microcontroller code I initially did, which I'll be showing you, everything runs here, and there's only power coming from that. It also has a battery you can have put in here for time for the clock and that sort of thing. So the Teensy, I had this in my shelf for a few years, $30. I bought it and Sergey's using Teensies a lot, or somebody, and I'm like, okay, I got to buy a Teensy. And then I'm like, oh, I want it for this project because it's extremely powerful microcontroller, hundreds of megahertz, clock rate, huge amount of RAM. It's really great. This is and it can handle a lot of peripherals and a lot of I/O. This is the MPU, very inexpensive for your accelerometer, etc. We won't talk too much about that. This is the GPS for more, for the more advanced project I'm doing. I won't be getting into the code for that this time, but that's the main components. And then go back here.
A quick question about your IMU. Have you got the compass working for that one? 'Cause I never got that working for that chip.
Yeah, in an earlier project I used the compass, not this project. If you go back to I had a little walking robot, the Otto. I used the compass for that because I was having trouble trying to getting the accelerometer, not the accelerometer, the gyroscope. They always have drift, and you're supposed to tune it, keep it stationary. And I was in a hurry, and I didn't want to learn or whatever. And so I'm like, I'm just going to use the compass. And so I set it up with the compass, and I had the robot walk a straight line by, checking the compass direction. So it does work. But it's subject to all the magnetic problems that you get with magnetic. Yeah, magnetometer. But I put it on a wood table, away from everything, and it was able to do something reasonable, walk that straight line, and it would stop and take a measurement and turn. But yeah, I'm putting it in here for the ROS implementation of micro ROS, which is what I'm running on here now. I won't talk too much about that. This is an intro course, so I'm not going to talk much about micro ROS, but micro ROS uses the code I've been given that's available in the Lino robot code base, uses the IMU and has support code and drivers for it. So you hook it up and it publishes an IMU topic in ROS, and that helps the whole system know where it is. So here, I whipped this up last night with the rough, or with the essential wiring, and using the fritzing. which I've always kind of wanted to use and never really used it. So here are the 3 servos that are on board. The ones I added are the pan and the tilt for the camera, and this is the steering that came with the truck. And so, and then very importantly, this here is the receiver, or yeah, receiver is this block of connectors, and that's what was under that plastic or rubber connector. This is the real hack to your device. And oh yeah, I'm going to get into how you find out what kind of signal you need here. So this is now in the original, the stock robot you buy, these are connected directly to the steering and directly to this thing, the ESC, which controls the motor of the robot. But I sort of hacked it and inserted these electronics, this teensy, to now do the control itself instead of the RF. The RF, when you use your remote control, the signal is coming through these pins here, and then goes to the steering servo and goes to the motor ESC. So I'm hacking in, and I still wanted to keep the remote control signal so that I could have a manual mode. So I am able to use the original remote control if the system is in manual mode, and I forward those signals. So you can use it just like the original device. Or if in automatic mode, it's the software takes over and can run the system as it sees fit. And in addition, there's an emergency stop feature where here's the remote control in my picture, my videos here. The RoboMagellan course and other contests require you to have an emergency stop switch. So in this case, when it's in automatic mode, I have to keep the full throttle on, and if you let go, the robot stops. And so that's why I kind of wanted to use this as a multi-purpose thing. In manual mode, it controls the robot as a normal RC car. And in auto mode, you must hold the switch on for the automatic system to be able to move the car.
So for anyone doesn't have a lot of experience with that, why wouldn't you just do it the opposite way? Why wouldn't you just have a button to press if you want it to stop? Why do you have to hold it down?
Well, they call it I hate to use the term, but the deceased man switch is a way that if if something happens, the car goes out of range, or for whatever other reason, it has to be the other way. For an emergency stop, it has to be loss of the signal rather than gain of the signal or sending the signal. Because what if your signal strength is dead, your batteries die, you're out of range? The robot will keep going if you need to send it a stop signal. This is a keep going unless, this is basically, if you don't receive this keep going signal, stop. That's the concept. So, so that means I have to, on a contest, I have to keep within distance of the remote, or the robot will stop. But in this contest, I'm trying to make the software so that if a child runs in the way of the robot and you stop it, then when you clear the scene and resume, the software must be able to resume without getting confused. So that I'm working on. In ROS, it's going to be an emergency stop topic, so that it will send this topic just in case. I don't know if I need that yet, but I'm going to just publish that because it's easy enough, so that so that the system knows when emergency stop is activated. So it doesn't build up like an acceleration, like, hey, I'm not moving. It must be a really sticky ground. And and goes up to full speed, and then when you turn it on again, whoo, it zips away or something.
That wouldn't be a simple if-then statement or something like that, if else,
Or
to code that.
yeah, well, I mean, if there, as long as the system knows that there's an emergency stop happening, but right now it's at the microcontroller level. There's no, the upper level system does not know it's just been stopped. You know, it doesn't have any idea. It just knows that it's not moving. And then therefore the upper level system might say, put more power in because I'm not moving. It's like in a animal, it's as if you touch a hot stove and you know how if you're familiar at all with if you learn biology in high school, whatever, they put your hand on a hot stove, there's a signal goes to the brain that you pull away before you're consciously aware. That's what's happening here. If I let go of that, there's no signal going to the receiver and the microcontroller, so it immediately stops. The Raspberry Pi doesn't even know that's happened. And all the upper level coding for navigation is on the Raspberry Pi. So it would have to be told, hey, by the microcontroller, hey, I stopped. So don't ask me to keep going, you know, or get, you know, don't try to accelerate me.
As long as your TT's working.
Yeah.
It's kind of like.
Well, the teensy code is, yeah, the teensy code is you know, always, of course. But if the teensy code stops, then the robot will stop from the hardware point of view because there'll be no PWM being sent, and the ESC will start blinking, saying, I don't know what's going on, and stop.
Jim, when you're holding down the trigger, that's sending a signal, right?
Yeah.
How do you keep the electronics from fighting, your micro fighting signal? You have a relay or something that breaks it when you're you know what I mean? Because you have two different things. One, does the microcontroller know it can fight against the
There's like I said, there's two modes, auto mode and manual mode, which is set by a variable, I'm going to make it an actual physical switch eventually, but right now it's a variable. When it's in manual mode, then all these signals, then the remote acts as a normal remote. It will send the signals to the motors and the steering as normal, as the original product. And when it's in auto mode, then the emergency stop, then this is only used for emergency stop only. Does that answer your question? So there's no conflict there.
Yeah,
It's one or the other.
I think, so there is no physical connection between the receiver and the servos. It always goes through the microcontroller first. So it reads it and then it writes it back out. So
Yeah, there's a
there is
forward,
no
there's
two
a,
at the same time.
yeah, if I didn't make that clear, there's, when it's in manual mode, the microcontroller receives these signals through that RF receiver, and then it's actually through an interrupt code. I'll get into that a little bit. It sees the signal coming in, analyzes it, and then forwards that PWM to the actual motor in manual mode. So I was gonna, people have suggested you can use a hardware electronics, a way to do that, with some NAND and AND gates and whatever. You could just use gate logic. But I thought, oh, well, I may want to capture the steering in the software so that I can use clone training, for instance, in the future, where I drive the robot around the track, all the steering data is captured. I use AI to train it, and so I thought, okay, if the software way doesn't work so well or causes problems, then I could always go back to a gate logic where it simply forwards the signals through, a single switch in gate logic. Says it's a select, like on a chip select, so it will say send this or send that. But I haven't done the hardware solution right now. The software one is working fine. So in the future, I might do that as another way. So this is the same thing you looked at. This is a less friendly looking, so I won't. But this is the same as this one. Okay, what I wanted to, gonna get, so that's the pictures. Now, I want to show you, essentially how these systems work. The car itself, uses PWM, pulse width modulation, to control the motors, both the steering and the drive. And so the first thing I did was, although I probably didn't have to, because you look on the internet and it just all matched what other people have found before. But, I did the exercise because I didn't know for sure what the signal widths were and that sort of thing. So I hooked up to an oscilloscope and plotted it out, or got it to go, and actually put my probes on the output of those receiver lines that go to steering and go to the ESC. And you can see this one. Let's see, where's the name of the file? So here's, well, you can see the names of these. Backwards full, steering full left, steering full right, steering straight. So if we look at these, this is the steering full. What are the names of the file? It doesn't say. Oh, I guess there. Let's not go max screen then. So at the top here, you can see the name of this. This is backwards full, and you can see this width, and then the forwards full. You see the forward full is this much wider one, right? And then neutral is this one. It's in the middle. So backwards is that, forward is that, and neutral is there. So now you kind of know what the width of these this pulse width modulation is. This is essentially taking a digital signal and turning it into an analog for the device to, that device is expecting analog, kind of a certain amount of work signal coming, and that's how you provide that voltages by changing the width of this digital signal. It's simulating an analog amount of voltage to control the amount. And so, and the same thing with the steering full left, then steering right is the wide one, and then neutral, which is straight, is this one.
So Jim, if you could go back to your full backward slide for a second, there's a very interesting point when you look at this with an oscilloscope. And if you could embiggen that a little bit. So when we talk about traditional servos and sending them servo pulses, those pulses have a certain width, and that width of that pulse means something. Now, looking at Jim's screenshot, if you move it up just a little teeny bit, or move it up a little bit so you can see the bottom of it, we can see that on your oscilloscope, each square, the width of each square is 250 microseconds. And so what that tells us is that based on how the pulse is framed, this is perfect. We can see that when it's a full backwards, the servo pulse to drive that is 1,000 microseconds.
It says right here, 1.0 microsecond.
Yep. That's perfect. And when you look at
This is nano, this is micros, 250 microseconds, 4 times that is milliseconds.
oh, 1 millisecond, okay. And so when you dig into the servo object in Arduino or under the covers and how they do it, that's exactly the only way you communicate with the servo is by sending a pulse between 1 and 2 milliseconds or 1,000 and 2,000 microseconds. The exact ones vary a bit when you get down deep and dirty, maybe as low as 500 and maybe as high as 2,500. But that's a great shot that shows exactly how you communicate with servos just by reading the oscilloscope.
Right, that's yeah. I don't know if this is kind of you know, if people already know all this or,
I'm sorry, I'm just geeking out on the,
or if
graph. I love
people,
graphs.
don't know about this, but yes, I'm trying to, you know, do the best I can for the general audience.
Ross also has a question for you. He was wondering what IMU model that you were using. He's working with an MPU 9250 right now.
Yeah, it's a 9250 clone, from AliExpress. It's technically it's like 9265, or it's a, you can get it for $5 or $3, but it's a 9250 compatible.
Thanks.
Yeah, and those are very convenient because they're small and they run on very little power. And in fact, the ROS community seems to love them because that one was supported, you know, out the gate by the micro ROS Mino robot code on GitHub. So, so yeah, that's that. About
Yeah,
the captures.
It was a good one to use because the first time I tried it, I burned it out for somehow or other. And I got another one from Amazon the next day for a couple, you know, whatever it is, $5-10.
Oh yeah, they're very good. I mean, they're very inexpensive. Yeah,
And it seemed to work. I mean, as far as they talked to the software, I haven't got it verified with doing anything useful, but anyway, thanks.
yeah. So, oh, let's go into this now. Just to show you some of the links from the Traxxas site. You know, you obviously want to know about the electronics, so you can look up, you know, the different, well, obviously the dimensions of the robot will become important later, and then the ESC and what power it can provide. Actually, the ESC isn't as important as whoops, what happened? Oh shoot, did I not? I didn't plug in my power here. This is we call it the DAV tough, ASUS tough.
See a lot of that's on.
Yeah, it has the 6 gigabyte, you know, NVIDIA or whatever. Sorry, so yeah, yes, you want to know, for instance, I wanted to drive some more. This is about hacking, so I wanted to drive more some of my own servos, and the that receiver and the ESC, they provide what's called a battery replacement circuit, BRDC or whatever, and so what that does is it already has like a buck converter that takes down the LiPo battery down to like 6 volts, because that's how the system powers its own servo, its own like steering servo. And so I wanted to connect some more servos, and I was like, do I have to power them with my own battery or not? And then I looked it up, and you know, the official number was like 1 amp for that circuit, but you look up the unofficial and it's 3.5 amps. So it's fine, and it's been tested on that. So, and of course my 9-gram servos, 2 more my 9-gram servos are not, plus the steering are not going to tax that too much. So I felt very confident in adding those other 2 servos to the ESC, essentially to this battery replacement, and in fact, that those pins are made for additional servos. There's 3 channels there with two channel 1 rows, and then a channel 2 row and a channel 3 row. And those are all for RF. This is only a 2-channel RF. So the 3rd row is, you can, you can use that for whatever you want. And the 1B, the 2nd row, as well. All right, let me get back online here. Does anybody have any questions while I'm getting back about the hack?
Yeah, I'm gonna lay off until after the Robo John, but I'm very interested in hearing about your experiences with the compass portion of the IMU from within the framework you've mounted it. Because I'm gonna run into the same thing on Alfie, and I'm not sure if I'll get anything useful out of it or not from the base.
Oh, yeah, I mean, my plan right now is I'm not even working with the compass. I'm just gonna use the GPS.
Oh, yeah, okay.
I'm not going to probably do much with the compass, but eventually, maybe at some point. Okay, here's let me get back the link. Because that's a whole other, there's a lot more to talk about.
When you pass your input through the microcontroller first, does it create any input delay on the manual mode?
No, not really. Again, that's a good question. What is interesting about this is, okay, I'm back on here. Is that, and I've got to quickly move to a little bit of the code part of it. Is the code uses interrupts. The Teensy has many interrupts, the hardware level interrupts. So I found this code online, and I have a bunch of links. I guess I'll share later, but I can show you 1 or 2 of them now. But with a hardware interrupt, it's real-time analysis of this incoming signal and real-time sending out. So there's no noticeable human time delay at all. And
The PWM is going at 100 hertz, which is pretty slow, and the microcontroller is 600 megahertz.
yeah,
So
no
you won't
possible.
say anything
The
there.
Teensy is
You won't
very,
do it.
very powerful. I wouldn't use an Arduino Uno on something like this, probably, but other or where's the John? Web links. This is the thing I've been talking about, the receiver, and this is where I plug in my servos for the this is where the steering servo would normally go, and the drive motor or the drive signal comes. And what's interesting is the power is actually coming from the ESC into here. So that's and then so the power comes from the ESC, the 6 volts, and then also the signal goes the other way from here to control the motor itself. But this whole unit is powered from the ESC coming in. So I still have to keep that line in. And the grounds I had to tie. So you have to tie the ground of my battery and their batteries so that the signal will work from the Arduino or from the Teensy. That's an important aspect, ground tying. And let's see, so I won't, so you look up the specs of this thing and you can, then like I said, I found out it certainly already has 4 ports here. So I just put in 2 more servos on the load of this, and they're just small micro servos anyway to move the camera. And yeah, you can use the documentation of the from Traxxas itself to make sure you're working with the electronics safely, and that's something obviously I did recommend doing that. And yeah, there's different websites this is the main website. And then I was clicking on electronics. And yeah, and then I won't go too much in it. And then there's the owner's manual. I would look there as well for any info you need about that. And then so yeah, let's move on to the actual code here briefly. So this is I'm using platform IO within the system of VS Code, and VS Code platform IO is an alternative to your standard your standard Arduino IDE, and I'm really digging it nowadays because it's got, as Alan will testify, it's got so many nice features for parsing your code, as well as the Copilot, and I use Copilot as well, GitHub Copilot. But yeah, the core is here, where you can see that now out of what you saw there in those oscilloscope, this is the actual numbers. The neutral PWM is 1500, full forward is 2000, and then reverse is 1000, and full right and full left. And I didn't want to go 100% full left because it makes a sound. It's like, I think that whatever they might have mounted it slightly wrong or small.
Yeah, and they're not exact with servos. So like we want everything to be perfect with 100 is exactly 90 degrees to the left, but between the potentiometer and how it's mounted and how it's glued and imperfections in the components, it's never exact, which is fine for left, right, like when you're just steering it, because your closed loop is your eyes, right? You adjust it, but when you talk about robotics and stuff, you're like,
Yeah, well, I'm using the steering as is. I'm not going to replace that, but this in the full system with ROS2 and NAV2, and GPS and IMU, and encoders. I didn't talk about encoders. I don't have them on the wheels. Some of the other guys here do. I will put those on after this contest. I just don't really have time right now for wheel encoders. Like a homemade solution that Justin put together, Brian's nephew. Anyway, but for now, I will rely on those upper level systems to determine where the robot's going and correct the steering in a closed loop through the ROS, basically ROS navigation. So then, this is basically, I just go through the high level, manual mode, auto mode. And to facilitate manual mode, we calculate the throttle, we'll calculate the steering. That's figuring out what the PWM coming in is. And then these other things are like get to steering by like a percent instead of like a percent. 0 to 100 is much kind of easier to deal with in most cases than the PWM signal. I don't want to think about that. But you can see this is a traditional Arduino setup and loop functions. And you can see it's setting up this is the e-stop pin. And then that's like critical, as I said. And then there's the throttle and the steering, which are both using the regular servo class, which the servo class puts out the PWM that I need, really, or even though it's going into one of them actually goes to a servo, the other one goes to the ESC, which is then converting that to the right voltage to the actual motor. It's the velocity, it's the control of the motor. So that's, you can use the servo class in Arduino.
I think we just lost the camera.
Walter, I think your foot just disconnected the.
Yeah, I see.
Let me know if you can, if this is too small still, or can you see, can the people online? see?
Yeah, true.
Alright. And then, when this system is running on the Teensy, this code all runs on the Teensy, so the Teensy has an LED, and it's nice to use that LED to tell you what's happening with blinks or whatever. So you can set it to blink for error codes or for when things are working normally. And so that's kind of a good use of this. So I have it flash every 500 milliseconds. And that's using a timer, and which is available to you just through the libraries. So this program uses the servo library. It's also, that's like the main one, I think. And in the main loop here, we're going to support manual mode and auto mode. And so the auto mode, so now this one was set up, this code was set up to be for testing with the keyboard. You can control all what's going on. So that's why I have this whole, you type R to turn right, L to start turning left and forward. And each of these like increases or decrease, increases the throttle, or decreases the throttle, it increases the leftness or the rightness, which is really increasing, decreasing, and then stop. And for steering, I'm sorry, S is to steering straight, and then neutral throttle is in, whatever, it's whatever you want. And then a way to switch between manual mode. Manual mode then will just use the remote control like like the original product. And auto mode will, in auto mode, these letters do something. In manual mode, those letters don't do anything. Only the actual remote in your hand controls the robot. And so, as I said before, I won't get too much into this code, but the key thing is that there's an interrupt I think you saw that at the beginning here. The interrupt's installed so that right here, interrupt for throttle pin is always present. So this allows when you actually are using in manual mode, as soon as the signal changes, basically as soon as there's a change in that, if you're looking at an oscilloscope, as soon as the voltage goes up or down, this routine gets called, or a routine gets called calc throttle, and that's a hardware interrupt. So the Teensy is looking at 400 megahertz at that signal coming in, and it's only 100 times a second anyway. So as soon as that thing goes up or down, this routine is called, and therefore then I measure it. I'm measuring the length. So it goes up, I start a timer, and it goes down, I stop. So I've measured the width of that, and then I forward that width. And the same happens for steering. But I only need one interrupt, so you can do both of them. Or actually, no, I think anyway. But so that's any questions about this? Is just a quick review of now. There's what's nice about, or what's also to point out is that there are good resources online that help me get going on this. And that's where I started. I did modify from there, but can't remember if I have the links.
Oh, hey, Jim, I must have missed it, but what is it that triggers between manual mode and auto mode?
Well, in this initial script, this initial code that I did to test the system, it's use a keyboard on the, use a keyboard and, through your.
Oh, no, but I mean like on the remote, because that's only a 2-channel remote. How do you trigger that auto between auto and?
But to change between auto and manual, it's not on the remote. You
Oh,
have to
when
do
it
some
sends
other
the
way.
signal from here, then it knows to go into manual mode?
No, manual mode is through other ways. It's not through here. It's either through the keyboard or through a ROS.
Oh, I
socket.
see. You still have the laptop override.
Yeah, I have a laptop.
Okay, not the remote override. Okay. I
There's
got it.
no,
There's no trigger on the button on the remote to.
no,
change it.
no,
Okay.
what I'm thinking of adding is a physical switch on the robot to switch, because when
I see.
if I'm at Robo Games, I will drive it around manually to get it in position.
Mhm.
And then I go up to the robot and switch to auto, and that also tells it to start the race. So I'm going to
Right.
add a button on the robot, so I don't have to go in the laptop. And
Yeah, because that was what I was thinking. Laptop would be too inconvenient. So.
it's kind of inconvenient.
Yeah. All right.
But yeah, I don't have both of these channels are in use, one for
Right.
steering, one for throttle.
Yeah.
So there's no, if I had a third channel, if I get a new remote, and then I redesign, I
I could
could
easily swap it. They have like 6-channel remotes and you can do multiple.
Yeah, but
It's super easy to change.
I don't, I haven't got into that. My receiver only has 3 channels. So, and
I gave a presentation to the radio.
I
master,
should
but
do
they
this.
feel
Yeah,
all
that was
You
a
could
good
basically
one,
do
yeah.
15.
15.
If you were to
Oh my
change
God.
both at the same time, change your receiver
Oh,
and
yeah.
your
Well,
controller at the same time.
okay, yeah, but one cheap thing I could do is just buy an upgrade to this that has 3.
That's what I always do.
My thing has
Yeah.
already got 3 channels on the
Yeah,
receiver. So that I don't want to have, so I wouldn't have to replace the receiver
Yeah,
on
even
the.
like a 6-channel is like $35. They're not expensive, but his is like amazing. He's like the top of the.
Yeah, I mean, I want something, of course, that fits under the hood of that in the same,
Yeah.
footprint as the old one. But, I would at least upgrade to a 3-channel. And if there's a way to upgrade, maybe I could upgrade to a 6. in
That's
that
what I
same
did.
thing.
Actually, last night I did that. I swapped one from 2-channel, the Traxxas, to the 6-channel.
Yeah,
Last night I did
yeah,
that,
so
yeah.
I have to you buy a new one of these. and
It
a
comes
new-
with the receiver, yeah.
Oh, it's like one
It comes-
price.
This is a package, yeah.
Yeah, so that's an idea I will probably take on,
Yeah.
definitely late at a point.
You could use the aircraft style ones if you wanted to, right?
Well, that's what.
It can, but it's kind of hard to control a truck with the RS. I've done that too, and I don't like it, but the pistol is the best.
I got a van controller, so it's got dual skin, but it's got 15 channels, all the switches everywhere. But it uses a different protocol, so you have to deal with the other protocol.
Yeah, but I've done it both, and I prefer the pistol for an RC truck like this.
Yeah, I've never used one.
Yes, that's, a lot of these guys here have, more experience than me in this. I'm kind of fresh into the RC car modification. So yeah, I can use advice, on the future. Right now, it's kind of I'm getting the basic thing implemented.
Oh, yeah, one more thing, like the remote that he was showing, some of them provide feedback on like the battery level and everything, right on the remotes, so you
Yeah.
can see what's going on with your truck itself. It's very nice.
I'm always wondering if my battery's.
Yeah, so that's another thing you can
Oh, here it is.
look at it right there.
Yeah, so you just have to set that up on both ends and you can, so this project that I'm working on has it's a beginning of a long-term project that has many upgrade paths. Like they're talking about even the low level, and then of course the raw side is there's so much, capability there that you can add. So this guy, Eric Maggard, produced a 4-part series of building on autonomous car. I used this for part of mine. In fact, that's where I started with, and it's very helpful. And he got into the signal measurement. I could write one of these. I should maybe write something myself for my experiences after doing all this. And
You
so,
definitely should.
because I kind of he was using ROS1 and some slightly older stuff, but some of his code, I ended up using in that code I just showed you. And he explains how to do that, that interrupt. Or I guess
Right.
mainly the code explains
Yeah,
itself, but
that's a good one to have there.
but yeah, here's the idea is, this is the delay, by the way, between when the signal comes in and when it's going out. You can see it's in a millisecond, very, very quickly does the input from the controller, and then it's measured, and then the output from the teensy. And so there's almost no delay. And so, yeah, that's how we're doing. Okay. So, so that's some good resources. I'll post some more of those. If they aren't posted by Alan or somebody. And, so yeah, anybody have any questions about any of this?
So you're using Micros to facilitate the communication between your Raspberry Pi and your Teensy, right?
This, yeah, exactly, in the other code.
Okay. And so on your RC car, basically you've got like forward, backwards, and steering. That's what you're trying to control. What ROS messages are you using to facilitate that? Are you using Twist or as a custom message format?
Well, the command velocity is the name one. It's command velocity has.
Is that a standard?
That's standard ROS message. CMDVEL is what the in fact, I'll do it if I have a chance. Sign me up for, if my router is working here, I will do a demo of controlling the robot from ROS. Manual control. So essentially it's a it uses command velocity, and inside command velocity comes with a twist, and which is an angular velocity and linear velocity.
Gotcha.
Both of those.
So this is one component of it.
Yeah, they're all command velocity is the top, and inside there's a message for twist and a message for the velocity of linear and angular. And so if I am able to get it running later, I'll show you this GUI that they have called RTT steering, which lets you use sliders and adjust the throttle and the angular velocity. And then your robot will drive.
Can we include the rest of your talk to the show and tell, because it is.
That's it. That was gonna be show and tell.
So thank you, Jim.
So thank you. Yeah, thank you.
All right.
Oh. Which one? You mean in the code or somewhere else?
In your photos and your code.
Okay, thank you. Yes.
All right.
You do a
I
very
can do
good
more.
job.
So Sergey
I
was
appreciate
first on show and tell, but he looks like he left. So Walter, you're up.
Well, I did this one last month, but is the camera working here or no? Not anymore.
Yeah. Oh, wait, is it turned back on? Plug it back in.
Back on, but it's not.
Let me, see if I can.
Should I close it and open it again?
Yeah, we're live.
Oh, it works. All right, well, I showed this last month, but I brought it so that Catherine can actually see it.
I didn't get to see it in person.
That's right, yeah. All right, so this doesn't have much fancy code or autonomous, but it does have some code actually. But let me see if it even works. I just fixed it last night. This is another kind of RC control, by the way. This is a tiny, control. It's got six channels in there.
Want to show it on the camera?
Oh, yeah.
For those
There you go.
those watching from home.
Tiny six channel remote control, single hand. So you don't have to worry about using two hands. You can go forward, back, and you have four other functions in there. So last December, I went to a Comic-Con. I like to build like Star Wars kind of stuff, or this kind of thing, like more entertainment kind of robots than the autonomous robots, because
still like almost the same for a year. I noticed that it hasn't really changed. It's changed, but it really hasn't changed. So I figure I do something a little more entertaining and artistic. So I went to Comic-Con last year in December, and then I saw these guys with backpacks like this. And I saw them walking around. They had like uniforms, they looked like mechanics, and they had these little backpacks, and they have like little Star Wars robots in there. And I thought, man, that is so cool. I like that idea. Very creative, and they were all painted like this and everything. So I thought I'd give it a try and do my own. And so I did. So this is a carrying bag for a cat. So you buy this on eBay for $29.99. And it's just, you put a cat in there, and it's got a fan and lights, and you can carry your cat anywhere you want to with it. And so I got that and, painted it and all that. But then I thought, okay, what else can I do to it? So I added some wheels to it because it's heavy actually. Once you start putting these little toys in there, it becomes pretty heavy. So I thought maybe I'll just add wheels so that it can actually move on its own, and it's actually heavy. And then I thought, well, why don't I make the entire bag be a robot or a droid, as it's called in Star Wars, and then have it carry other little robots in there. And so I did that also. And this is what came out of it. It's a backpack that is a robot that carries other robots. And yeah, so it can move, up, forward, back, left. I'm an experienced puppeteer. I can drive stuff. I've driven RC stuff for years. More than some of you have been alive. So yeah.
Native driver, huh?
Oh yeah. I'm an experienced RC driver. Anyway, so some of the functions that I have in some of the channels that you see here are things like, I don't know if you can, the camera, I can see it here. Oh yeah, the camera kind of can see it. So I have this little droid here that is moving his head. Oh yeah, I should probably turn the
lights. You got the interior cabin lights.
Oh yeah, I can turn the interior cabin lights on. Yeah, exactly. Yeah, go ahead. Yeah, go ahead. It will be. All right.
Can you like
Okay.
just do one?
So I actually do have lights in him. There you go. That'll make it a little better for you. So because this is actually a robot itself, it actually has eyes in there. I don't know if you can see the eyes. So when he's on the ground, he's actually looking up at you. And it's got its own sound effects. And you have the little robots inside there interacting. And then you have this other animatronic guy inside here, kind of talking. Let me see if I can turn it to the camera. Oh, there you go. Well, the idea is, in the Star Wars world, this guy is called Babu Freak, and he actually does everything. So he's repairing droids everywhere, and so he's actually welding something on this R series unit here. And so you can see him welding something. A lot of bunch of interactions. But anyway, and then the last thing that I decided to do was added some rocket booster from R2D2 that you see in one of the movies. I forget which one it is. I know the guy who designed it for the movie, so he was very pleased to see that I adapted it to this guy over here. And so, anyway, so yeah, it's just fun. I don't know what to call it. It's just for fun. I don't do anything for a living, just for my own feelings. So
Have you gone into the park?
I did. No, I haven't. I'm going, May 2nd. I'm gonna bring it into the park. I like to excited park, by the way.
Oh.
They don't allow Bluetooth speakers, so the Bluetooth speakers like hidden in there with a bunch of stuff around it, so don't tell anybody.
Or do they not care?
Well, what happened was I left the original speakers of those little toys active, so I can say, oh, it's just a speaker that comes with the toys that you sell. So, you know, then I can turn the speaker on once I'm inside there, so. Anyway. No, I took it to, Con, 2 weeks ago in Anaheim, so thousands of people got to see it out of there. But I've seen a lot now, so.
We have their campus open.
Oh, yeah, maybe I'll take it over there, you know, after lunch or something. It's a normal day, but Star Wars nights.
So you're going the night through then?
No, just a day, but, you know, they close at 9 for the regular, so I'll be there till 9
Oh,
PM.
so you get almost.
I get almost part of the Star Wars night, yeah.
That's the best time to bring it.
Right. Yeah, so, let me see. I'll just do a quick open because I know people are hungry and probably want to eat something, but, it does have a Polulu Maestro in there to do the animation of the servos here. Because I wanted to learn how the board works, so I just a 6-channel one just to. It's pretty simple actually. You see a bunch of RC switches. There you go. You get a better feel of what it's like. So it's modular, so in case I need to test it and troubleshoot it, I can just insert it or remove it back. So you have multiple controllers Oh, yeah. So I have to open these 2 toys and basically pull out the signals out of all the sensors and all the switches and all the power. And then I have to basically wire it all so that I could control it with remotes. Bunch of relay circuits and there's a lot of stuff. A lot of remote switches. Yeah.
It's like, but the original toy does all those movements basically.
The original toy does all the movements. This one has a remote that does all the movements. So, but I tapped into the robot itself. And then this one does not have a remote control. So I added RC to all the functions for
It
it.
would just do something when you turn it on.
Yeah, you would have to like press the buttons that come with
button
it.
on the
Yeah.
body.
So I just tapped into those buttons.
But you're talking several servos per toy and
Yeah, there's a lot of motors in there, a lot of things.
sensors too.
A lot of sensors, and the sensors were tapped also and into. So it's got the original functions if you wanted to just use it as a toy itself, or you can, you know, override that with this thing. So
So I have a question. How do
Yeah.
you get this past the Disney lawyers?
Oh, he's not selling it.
I'm not selling it or making money.
Okay.
Yeah,
He's promoting their products.
Yeah.
I'm actually making people buy more of
Free
this stuff.
promotions, so, yeah.
Disney, you owe me, okay? Pay me. Give you my address for the check. Actually, I have done work for them, so it's okay. They already paid me for all this stuff, so in other ways. So yeah, so that's it. It's just, you know, I saw it and I thought, you know, I need to do something similar to it, so I did my own thing of it. So yeah, most people they, you know, they just paint this, add stickers, and then they'll buy one of those toys, and then they'll put it with the phone inside a phone base, and that's it. I mean, that's the only thing they do. So this one, I kind of went a little bit above, beyond the thing, maybe a little bit too much overboard, but that's so.
The group calls these things DEPs and it stands for Droid Escape Pod. So it's supposed to be like an escape pod that the droid goes in, it can, you know,
Fly away.
fly away or shoot off the
Yeah.
spaceship.
That's
Right,
like the
right.
side rockets, yeah,
Well,
that's cute.
most of them don't have the side rockets, only his has those.
Like,
Nobody.
Yeah, there's a whole,
There's a Facebook group called Droid Smith.
yeah, yeah.
And so I joined them actually, so I got an official number and I got a costume and everything. So yeah, so I'm gonna meet them for the first time actually at the park, May 2nd. But it's just fun, you know, and then you add your own color schemes and this head, this is a chopper body is called. This head belongs to a different one. So it's a mix of a bunch of, this is a mix of a lot of it. So it's not just, I just kept adding whatever I thought I wanted to add, I just added that, you know, every night. You work on it a little bit every night. There was no plans or anything. I don't even have schematics. It's just whatever came, that's exactly what I did at the moment. So I have no idea how I even wire everything unless I follow each thing of it. But yeah, so this a lot of hacking, yeah, a lot of hacking. Audio hacking.
Audio
RC
too?
Yeah,
Oh,
audio.
because you read.
Yeah, I pulled the audio out of the units and used the sounds that come with the units themselves. So like this one.
Figured out how
Yeah, I
to
pulled.
trigger.
Yeah, I pulled the audio and then I made a audio distribution board here and then I just put it into a Bluetooth speaker.
Was it hard, or would you call it a more advanced, level of knowledge to be able to do the hacking to, to get the functions working?
No, this is advanced. This is
Pretty advanced,
this solder two wires and
but
plug
as
it
far
in.
as the, getting it to do each of its sort of animations by your control, did you know? Was it easy to figure out how they were doing it and then you could replace their signal or that?
I didn't figure out how they did it. I just replaced it with my own thing. So,
But it was,
yeah.
as far as triggering the
It's just switches.
It's just switches?
Just
Okay.
switches that trigger
Oh, all right.
whatever buttons and sensors they have.
So it's a toggle, yeah.
Yeah, I think the hardest part was following the instructions on this remote on how to do mix mode for the tank steering. Although the controller board has I found out last night it has a mixing button on it, so I didn't have to do the mixing already. Anyway, so that's the beauty of a lot of the motor controllers nowadays. They come with mixing functions built in already, so you didn't even have to do any of this stuff. So, but no, there's nothing difficult about this. This is pure creativity, relay switches, RC and everything that a lot of us have done already. So, I mean, I say it's not difficult, but it's difficult. Well, after 30 years experience, yeah, it's easy. So, yeah.
We were talking about beginners getting into hacking,
Right.
This is a more advanced project that you can start. One toy,
Yeah.
one actuator. Right?
Yeah, it's just one thing at a time. That's how I did it. I didn't plan the whole thing at all. I knew I had to get the case. I went to Disney one day and I bought the two toys while I was there, so I brought them home and I'm like, I'm gonna figure out how to fit them in there. So, but then, the cool thing is that I'm able to slide this into the PVC pipe ports and slide it out. So it becomes pretty modular in a way. So anyway, so that's all. Thank you. Got a nice rechargeable single battery for everything.
All right, so up next, and the joint show is Alan.
No rush.
I know,
So
right?
cool to look at.
Oh, yeah. I like how you made it so you can take it out and then that's.
Yeah, that's
Well, holy, I'm when modifying a product like I'm doing, also same problems, like I need to.
Yeah, same concept.
I have these
Yeah.
wires now that weren't there before, and how do you get it to like be usable? Cause you modify the thing and, you need to still take the cover off and all that.
Oh yeah. I think a lot of people are scared to open their toys and break them and all that.
Yeah,
That's the
that-
first thing I didn't even turn them on. I opened them and modify them, and then I turn them on to see what they did.
I drove mine first because it cost $300.
Well, these things are $100 a piece, so each.
Oh, is that each Droid?
Yeah, that's the motor.
Yeah, they're not cheap.
It's about $600 for this back.
Well, we're
Not cheap.
No, but it's.
All right, so, quick update on Project Alfie, from an idea 2 months ago to hardware complete last weekend. Right now I'm doing what I'm calling the systems integration of the brainstem phase. So, using micro to set up the interfaces so that some higher level program or system can control the robot's peripherals, right? And so far, everything, knock on wood, has been going great. I have a couple of challenges though. And the first one I wanted to get in front of Brian and Jim and anyone else. The tires and the wheels that are part of the base kit, they don't have any filler. They're designed to be super spongy, I'm imagining, for rock crawling or whatnot. But with the amount of weight and the slightest amount of twist, and they just come off the wheels. So I'm looking for solid rubber options, 80 millimeter in diameter. I'm wondering if maybe I can fill them with a silicone. Will that cure? I've seen some people mention over the years that they'll use like an epoxy to seal the bead on the tire to keep it from coming off. But as of right now, anything that I do results in. So that's the one part I haven't solved for yet. What do you guys think? What did you see?
Why don't you go to a tire store?
Oh, like a place that does like Traxxas and more off-road stuff? Yeah.
So, yeah, I mean, they're not built for this. I was there are other ones, you know, they'll build it as like hard wheels, hard on the outside. I don't know how you can match it with this.
Well, I'm sorry, you mentioned the manufacturer or
Go build that.
so like Go Build It?
Yeah, go build that.
Or go build it.
Yeah.
That's a very good,
Hard stuff.
Servo City is their Vex competition metric line, so yeah, so Go Build it and Servo City are just two sides of the same
Yeah,
coin.
one's metric, one's material, I think.
they have very good quality products. I use a lot of their controllers and things.
But on your car, I mean, I've taped my wheels, keep them from squishing for odometry, and that helps a little bit. And
Yeah.
everything you do to it's gonna firm it up, but I don't think I would put RC wheels on that top heavy big thing.
Yeah, I just need something hard rubber. I'm never gonna get perfect odometry anyways. But if anything that results in the wheels not coming off will be a win. So I know I've got to do something. That's pretty tight.
Oh, those are designed for, 50-pound robot stuff.
So they're 80, the default ones are 80 millimeters. So perfect. Thank you so much. I'll look into these. So that's my first frustration.
You can also 3D print your own, Alan, with the TPU. Yeah.
You're not wrong. You're not wrong. My second challenge is I'm not able to communicate with the server board with the stepper driver that I have on the robot. So I've ordered 2 more because I'm not sure what the problem is. But other than the fact that I can't communicate with it, it's more than strong enough to hold position. It's actually on and energized right now. There's enough spare capacity in its torque or in its power to handle it holding something. And I'm actually curious, when I get the new drivers in, I'm going to try to reinstall the original smaller NEMA 17 motor just to see if I can get away with it. So far so good. I'm hoping over the next couple of weeks I'll be able to communicate with it and then be able to raise the shoulders up and down. The last piece that I'm dragging my feet on a little bit because I'm multitasking too much is the whole concept of e-stop, dead man switch, making the robot a little bit safer, right? So this is my first mobile platform. So there's a general servo driver that drives the wheels, and once the raw stack, that brainstem piece of it, the micro ROS is enabled, I'll be able to send, whether it's a full command velocity stack with twist and velocity or something else, be able to send move forward, move to this location. But if you can imagine, there's ways of approaching this where you say move forward and then it never stops, right? And it's top heavy, there's all these other concerns. So I'm trying to figure out a method of control, much like a dead man switch that's like, hey, when I lose connection, maybe stop moving. So the strategy I think I'm going to take, I was initially considering a heartbeat message from high up to down low that would enable all of the servos and all of the driver components. And then the loss of that heartbeat after X amount of milliseconds or a second just shuts everything down, to maybe using the controller command message. So I've got a fat controller command message that has position, velocity, acceleration for all the servos, and direction and position for the, like it's all one big message. So I could use that as kind of a heartbeat that says, hey, if I don't get a command message within X number of milliseconds, check what my current motor velocity is. And if it's 0, disable all the motors. And if it's some non-zero value, do a graceful ramp down, because sudden stops are just as dramatic as sudden starts when you're top heavy, right? You don't want to cut off power when you're in a full run, because we'll just whack. So those are my current thoughts on setting up control such that it doesn't just run away. Is there anything else you guys can
Reach out and catch it.
in more advanced ones, right? The brace your fall, right? You want to apply some force backwards or forwards. These are all great opportunities for future research. But for right now, I just want to keep it from running into a wall when I code something stupid. And it's like, this is the last command that I had, so I'll continue moving forward. It seems like the wrong approach. So I think maybe using the command messages as a heartbeat will get me closer. It still won't keep me from, on purpose, accidentally sending it into a wall. But at least with loss of signal or command or something weird happening, it has a shutdown.
So I love the idea of the heartbeat, but I'd like to see some creativity to go behind that. And I'd like to see you install something that looks like a heart and lights up and actually beats.
Yep.
And then, you know, it does all the control issues too. That would be really cool.
Yeah. Yeah, and that's actually one of the challenges. These WaveShare general driver boards are really cool. They've got encoder motor drivers, they have standard motor drivers, they've got serial bus servos, they support an OLED display, USB, like they are super sweet. One of the things that they don't have is spare pins for a second serial port to be able to communicate status. There's not even an LED that I can toggle on there, because with the Teensy, I have a literal Teensy heartbeat. It's a little command that runs that does a beat thing, and that lets me know when everything's working correctly. I've got the dun 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 dun, but then I have an error loop that flashes quickly. The micro ROS RC check thing,
Yeah.
the error loop for that flashes at 250 milliseconds. Just for the simplest way of being able to intuit when something goes wrong and how to troubleshoot it. But on the Teensy, you have extra pins for extra serial ports. So you can actually set up additional logging. But on these general server boards with the ESP32, every pin is taken up with a peripheral. So it's a little bit more challenging.
On the what?
Oh, the general driver boards that are the WaveShare ones.
The WaveShare serial, or it's
Yeah, every
bus
pin is
drive.
taken up with a peripheral. There's no extra pins that I can take over for second serial that I can.
Oh,
For more advanced debugging and diagnosis.
and you have to talk to those from the your Teensy.
Yeah,
And
yeah,
you
because
send it, it's a serial, that's what we saw today,
Yeah.
that this is serial communication, but it's just for motor, it's just for serial.
diagnostic, right? Because when you're using micro ROS, you have a virtual serial port over the USB-C cable. But
Yeah.
once you use micro ROS, that entire communication structure is set up for micro ROS. So micro ROS and messages and ROS.
But that is, micro ROS is running on your Teensy, but those other boards, they don't have a,
I don't have a second serial port, so I've got to be creative when I'm troubleshooting or trying to figure out why something's not.
right, so that, but what, even if you did have a port with the, those boards, can they run code that those boards aren't?
Oh, absolutely.
So you upload code to them too?
Yeah. So picture this, when you're doing your Arduino stuff, right? You use print statements in the terminal monitor, right? Just like you saw earlier with printing statements to the screen, hey, I failed, hey, I succeeded.
Right.
you lose all of those, that print F interactive, logging functionality outside of ROS once you use micro ROS. So having a second hardware serial port in UART is really,
Oh.
really helpful when you're troubleshooting, because micro ROS is,
Yeah, it's from the teensy, but
it's
yeah,
not for
yeah.
beginners. It's,
Yeah, because then you just have a blinking light. I have a blinking light and maybe a log file.
so far, that's the best I've been able to do.
But your controller board, or those serial boards, the boards that control the servos, is the bus. Those are just communicating. The one that you said is full.
Yeah, so they've got their own dedicated serial
So
port.
you open that serial port and send commands to the bus.
Yeah, for the bus, and
But
then,
there's no other, and you get feedback. Oh, right. But you don't actually upload code to those devices. So they're,
yeah,
but
it's
you
just
do get,
troubleshooting the micro ROS code.
so you do get feedback, and then you could blink the light or something. You could, if you could have another, well, you could use software serial from your teensy.
Yeah, if you were rolling your own micro ROS code, you could use one of the other hardware serial ports on the teensy to facilitate those debug print statements and stuff,
Right.
which is super nice. I just don't have that.
Wait, but what about ROS out? I mean, the ROS out topic, you could publish information
Yeah,
on there
assuming
from
your
the
microcontroller
microcontroller.
didn't crash and it brought your entire ROS stack with you, which happens a lot with the roll.
The thing is, like, yeah, for me, I have very little experience with micro, so I copied code from a known grid system and modified it minimally and tested each section. So it's like I don't expect that code to crash.
Yeah,
because
maybe we could brainstorm a little bit more after we grab lunch.
It's like, you know,
I definitely appreciate the.
Yeah, I was gonna say one thing. So you're talking about this heartbeat from your messages. Half your problems, your computer's gonna send the wrong messages. Okay, wired, they have to stop it. So if you have something out of band, if you have a controller out of band, I had it so if I touch anything, it stops. So it's probably good to have something out of band outside of this your ROS. stack.
like I'm
Wait,
doing.
messages, Yeah.
Mine, you know, this goes through the receiver on the car directly to the microcontroller. And if the microcontroller stops receiving, at a very low level, it stops. And I got that into micro ROS as well in the new code. So,
So
in my,
the heartbeat, you got the remote e-stop. Do you need a button on the robot? Because
big red button.
it's the same as the remote.
Yeah,
one,
got the
but-
power switches up on top.
Okay,
and there
so
might
so
be
you do have a
just-
switch there, okay.
There might be just enough room to have a dedicated.
So my experience is someone downloads code to the microcontroller and it just goes in an input loop and the robot crashes into the wall. So, yeah, I mean, maybe I'm a crappy coder or people I know. But, so having that physical switch on the robot is useful in those situations. And I've done implementations where we kill the power to everything, and it's kind of annoying because now you're powered down everything. So if you could at least cut the power to the motors, then at least the CPU is still running. So, and you need a less chunky switch and relay to make that happen.
Yeah, you can have like just a little keychain remote to kill the power.
Yeah,
Right.
that's the same as the dead man switch. Yeah, I mean, you're assuming that works.
Yeah, because we're mostly concerned about mobility, right? So if there's some small device that I might be able to put in here in line with the lines that power those motors specifically, like totally outside of the ROS communication.
Yeah, oh, yes, yeah.
That's a really good
Outside.
idea, Walter.
Yeah.
And they make ones for cars or just the
$7 on
machine
every
remote.
phone.
Yeah.
Have a fob,
Okay,
Yeah.
on, off.
Yeah.
Done.
yeah, that's good. That's a really good idea. All right, that's all I got. Hopefully I'll have more next month.
Yep, and you can hide it in your pocket, so if you're demoing, people won't even know that you're the one who stopped it on time. They'll think that.
Yeah, multi-channel.
Yeah.
Does everything.
I'm kind of, is anybody else? So I'm trying to get the, well, maybe I'll just show, because I didn't get the Wi-Fi set up with my thing, it's kind of hard to actually make it. Oh, thank you. Thank you for coming.
One quick thing, there's a movie that Alan and we worked on. It's a short film. And it's actually gonna be now shown premiering at the Man's Chinese Theater.
Yeah.
for the, Beverly Hills Film Festival.
I'm like.
So anyway, just so you know, it's a cool project and now it's gonna be out.
So you guys, I can't wait to hear about the competition. That's.
Right? Cross your finger.
Oh, that's going, right?
Yeah, we're so not ready. Well, I'm not ready either. I know ways we're not ready.
Take pictures.
Yeah.
Well, I guess
good
Big
luck.
Orange might be reasonably ready, because they worked on it for 5 years, 4 years.
So while Jim gets this,
Yeah, I'm gonna just,
maybe we can do it in, open mic thing. Anybody want to share anything?
Yeah, I'm not sure if you guys wanna hang out and build session afterward, grab some lunch and come back, or.
Sure, let's just break for lunch now, and when Jim comes back, or.
why, or, oh yeah, we could do that, or, I mean, yeah, it's kind of lunch. I could, oh yeah, I guess if I.
Do new people have any questions, by the way, or we didn't really ask them? Do you have any questions about anything about the club or?
Oh yeah, general club info.
Yeah.
Yeah, this is the, this is open
Glad you
mic,
guys
so
came.
that's the way.
Mike, any questions you have? We've been around for a long time, since the 80s. So.
What is that?
Different colleges, and this is the latest college.
They're not people's garages.
Yeah.
There's nothing inside of them, so they're constantly squished. So I need to find something solid rubber.
What kind of games do you work on?
I work for Forward. It makes like retro themed beat 'em up brawler games.
So I know we've got to fix that.
Retro?
Yeah, like Double Dragon style.
Oh,
Arcadey.
Arcade.
Yeah.
I like retro games, I go to this retro.
Yeah. Maybe. The ones they make now are just kind of seem to kind of have that nostalgic feel to them, but they have more modern, like, we'll use sprites for the characters, but VFX, that's, you know, not speech themes, VFX stuff. But when I was going to college, it's pretty much a coin toss between game development and robotics, so I did game development, and I'm like, all right, well,
I remember for my undergrad, my capstone project, it was a tower defense game. Yeah. We called it, it's called, Battle in the Hood. So it was you could either choose to be on the cop side or the gangster side.
How about you?
yeah. I went into game dev because I wanted to program behaviors for like enemies and AI in the games. So I was like thinking, if I did robotics, I would want to have artificial intelligence move robotics instead of me. So I was like, well, video games, it's similar, you're just not physical, you're in the real atmosphere.
Oh, right.
So I mostly do C#, half yet to learn Python. People tell me Python is easier, but because I've only learned C#, I look at Python and I'm like, you're missing a lot of things there.
Yeah, the thing is that since I have another, and it's like robotics.
very
Yeah.
All about.
But that's just how it feels.
It's like, I don't want just one solution, I want
Figure out where
multiple
to
things that
start
cover
all
the
this
same
stuff.
thing. Like,
Yeah, but I.
this don't be used.
Yeah, yeah.
You don't have to start vision, and they're done in you, they're all done, a lot of redundancy.
Yeah, I still have to figure out what all the get started.
Why are they going
Go with an Arduino or.
Oh, and where's?
Online.
Yeah.
Yeah, exactly. Everything you. All done.
Yeah, I estimate where you are, what the.
Yeah. And so I'm starting to get into
We go to
that.
the corner, I mean.
Oh, yeah, I do learn best by going in and getting a bunch of files together.
So right now, yeah, I'm working.
Oh,
getting,
okay.
The columns filter, take the IMU and the LiDAR data, Or well, it takes those, and it will take,
actually.
they'll take it and filter it and give
Bring
you
lunch or something?
filter those on
That and I go back and forth, and I'm like,
Usually I don't write it in there, that's the advanced.
Give you a longer version of.
Yeah, I don't. And I think you're looking for lunch, but I went to see if I could get here. I wanna get back home and.
Yeah, no,
and
it's
then
hard.
stuff and
It's
stuff.
either when you look at one that's already made and then.
right, I look for that online, too, I try to follow that too.
Yeah, I'll make sure that you at least have it built really quickly.
I'd like to study more about. A little bit of a basic idea.
But if it's already, if it's at least put together correctly.
But I think that's just kind of,
Yeah.
obviously.
Then after that, it's
not
just a matter of.
Oh.
Not what, there was something that, I should have. reached
Yes, then it kind of.
Yeah.
They never quite- I don't know what it was, so I have to go back. to
Couple
the-
more miles away.
Better residue on your
Shutting down that. That's
Yeah, so the common filter does that.
Average after anything like that.
Right, you don't have, the common filter don't have a million studies. Right, so I'll review it after, I guess
Experience.
if I can later. Oh,